All right, hi. This is going to be one last video about functions, or at least the intro to functions. This will be a quick one. We just want to have a basic familiarity with some of our basic functions. We're going to get into some other kinds of functions later on, but and I encourage you with these functions to go ahead and on your own, if you're not familiar with them, the best way to get familiar is take the function, evaluate it at some points, make coordinate pairs, plot those points, and you start to get a feel for what the graph might look like. Right? And then when we have these big picture graphs, they're really good for getting us to understand the behavior of a function. Right? Does it grow endlessly? Is it confined to some area? Does it approach some value? Things like that. But we'll get into those details later. So our first basic function uh, is just a horizontal line. This is the function f of x equals a number. In the case that I have graphed here, that number is 3. Take out this grid. So all we see is the axes and our functions, right? But here I'm changing the value, right? The meaning of this, this seems like seemingly simple, but the meaning of it, one way we can think about it is, it doesn't matter what my input is, right? Any x value I put into this function, right now I'm looking at the graph of f of x equals or y equals 5.3. So no matter what input I put in, the output is 5.3, right? And this seems fairly boring, but it does tell us something. It tells us whatever these represent, right? If this function is our two variables in the real world, it's telling us that the input doesn't affect the output, right? If I were to collect data, I mean, this is going to be something silly, and if my input was my bedtime each night, and my output was the distance between my home and my office, right? It's obvious those don't affect each other, but we would see that no matter what my bedtime was, the output's going to be exactly the same, right? So it can tell us that, or this represents the fact that the input doesn't change the output. The output is unaffected by the input. All right, our next graph to become familiar with, this is simply the function y equals x. The output is just equal to the input, right? Each point on this line, the coordinate pairs, the coordinates are the same, right? So that's our simplest version of a linear function of the form mx plus b. You could consider the horizontal line an even simpler version where m is equal to 0, though I think typically we're not. We can throw it in there. They're in the same bunch. All right, let's look at absolute value. Absolute value has, on the right side, where we're looking at positive inputs, what does absolute value do to a positive number? It does nothing, and you just get back what you put in. So it's exactly the same as the function we just looked at, where the coordinate pairs are the same. On the other hand, when you put in negative numbers, different than, so there's that graph where when you put in a negative number, you get the same negative number out. The absolute value multiplies that by a negative, it makes it a positive, and so you get the same value except now positive. So we get this characteristic V shape, right? It's our absolute value function. There's our parabola, right? This is x squared. Sorry, that movement is just me zooming in accidentally as I bumped something. So here's our parabola, right? The output is equal to the input squared. So at 0, they're the same. By the time we get to, let's see, 1 should be in here depending on, well, it's not quite hitting it, but they're still close to the same. This will grow in both directions, right? As we move away from the origin, we're getting larger and larger. If I zoom out, right, it's just getting larger and larger. Maybe I should put some numbers back in. There we go. That's better. Okay. So that's our parabola. One thing to note about a parabola, and this is going to go for any x to a power that's a positive number greater than 1. is that as you move, let's just, as you move to the right, let's say, starting from 0, the amount of change you get changes. So for instance, when I go from 0, 0, if I increase x by 1, the output is increased by 1, right? So we go from 0, 0 to 1, 1. We increase x by 1, we increase y by 1. But as we go from increase x from 1 to 2, also an increase of 1, we now go from 1, 1 to 2, 4. We've gone up from 1 to 4, so we're increasing by 3. If we increase x by another amount, by another increment of 1, so from 2 to 3, the output goes from 4 to 9, an increase of 5. So we've gone from an increase of 1 to an increase of 3 to an increase of 5, and this will continue. And so that's a property we should kind of keep relevant, that as we increase, the amount of increase increases, if that made sense, at least in the positive direction. It would be decrease as we're moving in the other from the negative side. The same thing holds for x cubed in the positive direction. It's only more dramatic. I'll let you run through those numbers yourself. Another thing to note about x cubed is that unlike the parabola, right, they're fairly similar shapes on the right-hand side, but on the left-hand side, because it's an odd power, negative numbers to an odd power come out negative. And so the graph is going into the negative direction, whereas the parabola went in the positive direction. And note with both of these that these are kind of the characteristic functions for a whole set of functions. What I mean by that, characteristic is a bad word to use. Let's say representative function. If I look at any even-powered function, it's going to have a similar shape, right? There's x to the 4th, x to the 6th. They will get flatter in the middle, between -1 and 1, and steeper outside there, but they have this same, U shape for all even positive powers. Similar thing for odd positive powers. If we put in something like x to the 5th or x to the 7th, right? They're very similar shapes. Let's change that color. At that original x cubed graph, but getting flatter in the center there and steeper on the outside. You can even think about x as being kind of the first one. It's got no bend like the others, but it has a similar kind of a idea going on. All right. And let's look at 1 over x. We saw a version of this, or a related graph, in one of the previous videos. Let me make its color different than the axes. So let's look at the positive side first and just think about it for a second. First of all, let's think about large numbers. Anything larger than 1. When you take a number larger than 1, you take its reciprocal, you end up with a number smaller than 1, right? The reciprocal of 2 is 1/2. The reciprocal of 3 is 1/3, and so on and so on. Also, the larger you get, the smaller that reciprocal is, right? 1/2 is not terribly small. The reciprocal of 2 is 1/2 is not terribly small, but the reciprocal of 1 billion is 1/1 is very, very small. So as we get larger and larger values, the outputs are becoming smaller and smaller. We're getting closer and closer to 0, right? The y coordinates, the vertical coordinates here, you can see by the time we get out to 12, are less than 1/10. If we zoomed way out, just grab a point there, you can see we're down near 1/100, right? Let's just keep zooming out for a second, move way out here, right? We can just see that those, as our x coordinates are getting larger, 780, our y coordinates are getting much, much smaller, 0.001 in this case, right? So that kind of explains what's happening on the right side. On the left side, as we get, if we're looking at values less than 1, between 0 and 1, the smaller the number is, the input, the larger the output. 1 over 1/2 is the reciprocal of 1/2. So when you put in 1/2, so let's see if we can find that right there, 1/2, the output is 2. The reciprocal of 1/2 is 2. The reciprocal of 1/4 is 4. So as we get closer to 0, the outputs are getting increasingly large, right? A very tiny number like 1/100th for an input has an output of 100, and a tinier number, 1/1000, has an output of 1000. And there's no end to how large we can make our outputs because there's no end to how close we can get to zero. 1 over a trillion, 1 over a trillion to the trillionth power, and a number beyond comprehension is going to be spit out. The number 1 over a trillion to a trillionth is going to spit out a trillion to a trillionth, right? Something that's just immeasurable, measurably, but I would say incomprehensibly large. So that's what's happening as we approach this the y-axis. The closer we get to it, the higher the values are. There is no point where this line intersects the y-axis because that would be putting in the value 0 for x, and 1 over 0 is not defined, right? Any division by 0 is not defined. The exact same thing happens on the left-hand side of this graph, except the positive values become negative, right? Everything works the same. There's just a negative sign in front of everything, and so we just have that side flipped, right? And then if we do the same thing but we square it, let's make these different colors, right? I'll leave them both up for a second. Red is the 1 over x. 1 over x squared is in green. We see a similar shape in this first quadrant, the right-hand side. Because we're squaring the numbers now, the bigger numbers, when we square them, get bigger. And so 1 over that gets smaller. And so you see the green graph is below the red graph on the right-hand side. On the other hand, when we take a small number like 1/2 and we square the denominator, and we square it, we get 1/4, and then we take 1 over 1/4, we get 4. So in 1 over x, when you put in 1/2, you get 2. When you put in 1/2 to 1 over x squared, 4 pops out. So our green graph is higher than the red graph below 1, between 1 and 0, right? But then it also doesn't spit out negative numbers. So it looks exactly the same on the left-hand side, right? So that shape is just reflected over here. Let's just quickly see if we did something like 1 over x cubed, we would see, again, very similar shapes, obviously somewhat different, but now negative numbers come out when you put negative numbers in. And this, if we kept putting in 1 over x to the 4th, 1 over x to the 5th, all these things, we'd see the same kind of shape with some slight changes with the pattern that when it's an even power, everything is positive, and when it's an odd power, we end up with a negative outputs on the negative side of our graph. All right, let's quickly glance at the square root function. I talked about this a little bit in the last video. So it's the same shape as a parabola on its side, but also only half of it. This is to insist that it be a function. When we talk about the square root, we're really talking about the principal square root, that there's options for the square root, a positive and a negative value, but we choose the principal one to be the positive one. If you want the negative one, you have to say that. So the square root of x means the positive square roots of whatever number we put in for x. And then finally, when we have a cube root, a couple of things to note. Cube roots can take negative inputs and can produce negative outputs. And so on this negative side, right, like we can't take the square root of -1, at least with real numbers, but we can take the cube root of -1 because -1 cubed is -1. And so you end up with somewhere around here, -1, -1. Or the cube root of -8 is -2 because -2 cubed is -8. And again, if we took, instead of taking the square root, we took the 4th root, we'd see something similar to the square root function. And if we took, instead of cube roots, say the 5th root, we'd see something similar to this. This graph is like the x cubed graph turned on its side. In fact, let's look at that. In the same way that, all right, let's look at both of these really quick. So the square root graph is the same as the parabola, except we can only take half of it to keep it as a function. Whereas the cube root is exactly the same as the cubed graph on its side, because we don't have this problem of having to just take half of it. I talked about in the last video, the reason we have to only take half of it is because we want the square root function to have just one output. If we took both sides of the parabola, if we also put in the negative square root, and we considered the vertical line test. This is if we tried to consider this as a function, the input 4, for example, would have an output of 2 and an output of -2. But a function can't have 2 outputs for the same input. And so we have to throw that out. We don't have this problem with the cube graph, because if you have a negative input, you have a negative output. This is related to the fact that the cube root doesn't have this problem of 2 outputs for the same input. And this is related to the fact that the graph of a cubic function is what we call 1-to-1. That if you look at this graph, for any given output, there's only one input that gives you that, right? If my output is, say, -4 or some number down here, just looking at the graph, there's only one point on this graph at this height, right? This vertical value. Or at 0, there's only one point at 0, or at 1, or let's see, there we go, at 1. There's only one point on this graph with an output with a y value, a y coordinate of 1. Because to the right, it just keeps going up. To the left, it just keeps going down. Versus the square graph, there's another point with the output value of 1. It's right over here. Land on it. There it was. All right, so there's 2 points that output 1. When we go in the opposite direction, what we'll learn is the inverse function. The square root, that means there's 2 outputs when we're going in the opposite direction. So we have 2 inputs to the same output in this direction. When we reverse the process, instead of squaring it, we're taking the square root. We have two outputs for the same input. And to fix that, we restrict the graph. But we'll go into those details a little more later on. Okay, so these are our basic functions. We want to just start familiarizing ourselves with them. We're obviously going to get more complicated in these. These are kind of the building blocks of a lot of what we're going to do down the road. Okay, that is it for this one. Thanks, everybody. Oops, I thought I was turning off recording. It didn't work.